Hello friends, welcome to my channel Miracle Computer Education. Today in this lecture we will study types of non-contiguous memory allocation techniques, paging in operating system. Paging technique जो है is a non-contiguous memory allocation technique जो permit करता है physical address space of main memory to be non-contiguous, whereas it permits logical address space जो है can be contiguous. Actually, paging technique में main memory is divided into fixed size blocks called frames or logical memory is divided into fixed size blocks called pages. And in this paging technique में size of page is kept equal to the size of frame. Now as you can see in this diagram, process size जो है is of 4 bytes and page size जो है is of 2 bytes. Therefore total number of pages जो एग्जिस्ट करते हैं इन लॉजिकल एड्रेस स्पेस आर 4 divided by 2 which is equal to 2 pages. Since main memory is of 16 bytes and frame size जो है is of 2 bytes, therefore total number of frames जो एग्जिस्ट करते हैं इन फिजिकल एड्रेस स्पेस आर 16 divided by 2 which is equal to 8 frames. Actually paging technique में it is mandatory to keep page size equal to frame size. In this paging technique में the least significant bit that specify the word within the page are called page offset. So in paging technique we split a process into equal size pages and insert them into frames of main memory. In this paging technique में let's assume that we have a process P whose process size is 4 bytes and page size is 2 bytes. So total number of pages per process will be 4 divided by 2 which is equal to 2 pages. Here as you can see process P जो है split into 2 pages that is 0 and 1 in which the numbers 0, 1, 2, 3 are bytes. Thus in this paging technique में जो है we have represented these bytes as 2 bytes per page, thus dividing the process. Now as you can see in diagram explained above, we have 16 bytes of main memory. Now here frame size जो है is of 2 bytes. In this paging technique में हम notice करते हैं that frame size और page size जो है should always be same, that is 2 bytes, so that we can divide a process into pages and then one page can be taken and fitted into the frame. It means that the page should fit in the frame as it is. Hence we can say that we have taken page size and frame size same always. Now number of frames जो है can be calculated by dividing the memory size that is 16 bytes by the frame size that is 2 bytes. So there will be 16 divided by 2 which is equal to 8 number of frames in main memory. Thus we can say that we have 16 bytes main memory, which means हम data up to 16 bytes को memory में store कर सकते हैं. I have named these bytes as 0, 1, 2, 3, 4, 5 up till 15. So 16 bytes जो है can be stored in main memory. Actually CPU जो होता है always demand byte it requires. तो हम इस byte को easily find out कर सकते हैं और give it to the CPU. जब CPU is executing the process, the problem arises that CPU is not aware of the paging concept used. Actually CPU does not know that you have created process pages and fit them into memory frames. Means among the bytes 0, 1, 2, 3 of process, if CPU says it needs byte number 3, this byte number 3 is in logical memory in page form. Thus we use a page table to map logical address 3 to physical address 9. Now according to this page table, page P0 जो है comes in frame 2 and page P1 जो है it comes in frame 4. So we have assumed that page 0 and page 1 जो है has been inserted into frame 2 and frame 4 of the main memory. Thus we can say that bytes 0 and 1 of page P0 have occupied bytes 4 and 5 of frame 2 and bytes 2 and 3 of page P1 have occupied bytes 8 and 9 of frame 4. Now CPU जो है is asking for byte 3 of page P1 So if we want to give byte 3 to CPU from main memory, it may be allocated in random, which means it can be stored anywhere in the main memory. So the concept of mapping comes into the picture. Now CPU जो है needs data, then it generates the address 3. So it needs a technique that converts address 3 to address 9 and gives that data back to the CPU. Now MMU, जिसे हम memory management unit भी कहते हैं, converts the address generated by CPU into absolute address or physical address. Actually, for this conversion, the MMU uses page tables, means every process has its own page table. Thus, हम use करते हैं a simple concept that every process has its own page table. Actually, number of entities in page table जो होती हैं is equal to the number of pages in the process. Here we have here a process has 2 pages, so there will be 2 entities in the page table. तो जब हमें access करना है a page of a process, then we should know the frame number from which to fetch the data using page table by memory management unit. Page number, actually page number जो होता है is the number of bits required to represent the pages in logical address space or page number. Second is page offset. Page offset जो होता है is the number of bits required to represent a particular word in a page or page size of logical space, or word number of a page or page offset. Actually, if we access page 1 of a process from frame 4, now if CPU asks for byte 3, then we don't know where it is located. So first we have to locate page number of byte 3 and then locate frame number through page table through mapping. Now I am discussing mapping process. Actually CPU जो होता है generates the address called logical address, which is very important. Actually logical address जो होता है is made up of 2 factors. First is page number and the other is page offset or size of the page. Now talking about page offset, actually page offset जो होता है is actually a word number of a page. Page offset actually is number of bits required to represent a particular word in a page or page size of logical address space. Now question arises, how much is the page size? Page size is 2 bytes. So how many bits do I require to represent 2 bytes? So we need only 1 bit, that is 0 or 1, to represent 2 bytes memory in a page. Similarly, if we have 8 numbers, that is 0 to 7. So 0 is represented as 000 and 7 is represented as 111, which shows we need 3 bits to represent this range. But if we want to represent number beyond it, then we need 4 bits. Actually, if my page size is 2 bytes, then I need only 1 bit to represent it, that is 0 or 1. Now number of pages is equal to process size divided by page size, which is equal to 4 divided by 2, which is equal to 2 pages. So I need only 1 bit to represent it, that is either 0 or 1. Now let's suppose CPU generated logical address 3. So to represent 3 in binary, we use 1 as page number and 1 as page offset, that is 1 in binary is equal to 3 in decimal. Now here I have assessed page 1 of the running process. Now we have 2 bytes in each page. I have to select either 0 or first byte to fetch. So page offset is represented as 1, which means I have to fetch first byte. In this way, if we go to page 1 and we select second byte in it, that is byte 1, so we have fetched this byte having logical address 3. Now to fetch this byte, we have to convert logical address 3 to absolute address 9. To convert to 9, we have to use logical address consisting of page number and page offset. Actually physical address जो है represent the location of byte to be searched in main memory. Actually number of bits required to represent the physical address depends on the size of main memory. For example, to represent 16 in binary, we need 4 bits to represent it. So in this physical address, the first one represents frame number and the next one represent frame offset. Here in this physical address we use 3 bits to represent frame number and 1 bit to represent frame offset. Now in physical address there are 8 frames 0 to 7, where 0 is represented as 000 and 7 is represented as 111. So we need 3 bits to represent frame number. But total number of bits required to represent physical address are 4 in number, in which 3 bits represent frame number and 1 bit represent frame offset or frame size. Thus the logical address 3 generated by the CPU has to be converted into physical address 9. To convert, we know that page 1 is mapped to frame 4 in main memory. Actually it is given in page table that page P1 is mapped to frame 4 in main memory, which is to be accessed. Now how we represent 4 in binary? 4 is represented as 100 in binary. Here frame offset जो है is also called frame size. Moreover, number of bits जो है जो representing page offset and frame offset should remain always be same. Actually we want the second byte of page 1, which is supposed to be located in second byte in the respective frame. Hence without changing the sequence we shifted the page to frame through some frame. So I need to fetch second byte, that is byte 1 from frame 4. Now actually 1001 is equal to 9, which is the physical address, where first 3 bits, that is 100 is frame number and last 1 bit, that is 1, is frame offset. Therefore we will fetch data from byte 9 and give it to the CPU. So in this way logical addresses is converted to physical address. As you can see in this diagram, CPU generates a logical address consisting of page number P and page offset D. Now as you can see, page offset D and frame offset D always remain same. Now here page number P is mapped to frame number F using a page table. Hence physical address is generated consisting of frame number F and frame offset D. Hence in this way logical address generated by CPU is converted to physical address in main memory. Now in this diagram I am discussing page model of logical and physical memory. In this model, page 0 is mapped to frame 1, page 1 is mapped to frame 4, page 2 is mapped to frame 3 and page 3 is mapped to frame 7 in physical memory as shown in the diagram. Now in this diagram, if the size of logical address is m bits and page size, which we also call page offset, is n bits, then m minus n bits are used to represent page number. Now I am discussing an example where logical address is converted to physical address. In this diagram, we use a page size of 4 bytes and physical memory of 32 bytes, 8 frames, and logical memory of 16 bytes, 4 pages. In this diagram, in page table, page 0 of logical address is mapped to frame 5 in physical memory. In this diagram, as you can see, page 0 consists of 00, which is equal to 0 in decimal as page number, and 11, which is equal to 3 in decimal as page offset. Now when page 0 is mapped to frame 5 in physical memory, frame 5 consists of 101, which is equal to 5 in decimal as frame number, and 11, which is equal to 3 as decimal as frame offset. Now as you can see here, both page offset and frame offset remain same, that is 11, which is equal to 3 in decimal. In this way, logical address 0011, which is equal to 3 in decimal, is converted to physical address 10111, which is equal to 23 in decimal. Actually each operating system जो होता है have its own method for storing page table. Most of the operating system जो होते हैं allocate a page table to each process. To establish this mapping page table, a pointer to page table is stored along with other details in the process control block. Actually, for good performance of a computer system, the execution of processes जो होता है must be very fast and does need a strong hardware support. A simple solution to make the execution fast is to use a special small fast lookup hardware cache called translation look aside buffer, that is TLB. Actually translation look aside buffer, that is TLB जो होता है is a memory cache that stores the recent translation of virtual memory to physical memory, or we can say the mapping of logical address to physical address. Actually address translation look aside buffer जो होता है is used to reduce the time taken to access the user memory location. It is also called an address translation cache. और जो address translation cache is a part of the chip called memory management unit, that is MMU. In this diagram, as you can see, CPU generates a logical address. If there is a TLB hit and translation of page number to frame number is present in TLB, then logical address is mapped to physical address directly through TLB. Otherwise, if there is a TLB miss, which means translation of page number to frame number is not present in TLB, then CPU refers to the page table and the logical address is mapped to physical address through the page table. Actually TLB जो होता है is used for ready reference and coordination with page tables in the following way. Actually, when logical address is generated by the CPU, its page number is presented to the TLB. If the page number is found in TLB, then it is called TLB hit, and its frame number is immediately available and is used to access physical memory. On the other hand, if the page number is not found in TLB, then it is TLB miss, so a new memory reference to the page table has to be made. So after getting the frame number, we can use it to access physical memory. Further, to update TLB, we add page number and corresponding frame number to the TLB so that it can be found quickly in the next reference. If the TLB is full of entries, then the operating system can make a replacement. Actually, the whole purpose of this mechanism is to make complete and efficient mapping of logical addresses to the corresponding physical addresses for effective functioning of the system. Actually, major effort जो है is to organize TLB in such a way that the desired page has a reference available in TLB. We estimate the hit ratio of page being found in the TLB. Actually, hit ratio जो है is the percentage of times that a particular page is found in the TLB. It means if hit ratio is 90%, it means we would find the desired page number in the TLB roughly 90% of the times. Students, आज हम हमारा टॉपिक टाइप्स ऑफ नॉन कॉन्टिग्यूअस मेमोरी एलोकेशन टेक्निक्स दैट इज पेजिंग इन ऑपरेटिंग सिस्टम यही एंड करते हैं. आई होप आपको मेरा लेक्चर पसंद आया होगा. अगर पसंद आया है तो लाइक करें, शेयर करें, बेल आइकन को प्रेस करें और चैनल को सब्सक्राइब करना ना भूलें. थैंक्स फॉर वॉचिंग गाइस. थैंक यू.